Well, welcome back after lunch. I have never tasted baby corn paisam. That was something new. That's what he said.
Something else.
Huh?
That is something else, Prof. I don't. It is not baby corn.
I asked him. He said baby corn. Anyway, we looked at Fourier descriptors. Fourier descriptors will have a number of values, as many values as in this given contour, and coefficients complex. But of course the input is also complex. So there is no data reduction, and we have that many coefficients. If you simply pump all of them in, there is no point into pattern classification. So it will be good to derive a few features or measures using the Fourier descriptors, and we will talk about one of them. Liang Shen, who did his MSc and PhD with me, developed a Fourier descriptor-based shape factor. First set Z0 to 0, and the descriptors are independent of position. Z0 is just a centroid, so we don't care where it is. Each coefficient is divided by Z1 to normalize for size, but that also takes away the phase. Z1 is complex, so if you divide by that, the phase is also the phase of that is removed from the phase of the rest of the components. So the magnitudes of the Fourier descriptors are independent of position, size, orientation, starting point of the contour after this, if you take the magnitude. The orientation and starting point affect only the phase of the Fourier descriptors. So by dividing by Z1, we achieve some more convenient properties. So the normalized Fourier descriptors are the Z0 K, 0 for K equal to 0, Zk over Z1. So for this, the points of the contour must be indexed 0 to n-1 in the counterclockwise order. In the opposite case, you should use Z-1. Contours with sharp excursions possess more high frequency energy than smooth contours. I showed that. Similar to signals. More rapid variations, more high frequency energy. Applying a weighting factor that increases with frequency leads to unbounded values. So when we take moments, we multiply with a weighting factor, typically increasing, and more high frequency will say, well, put a weighting factor that is increasing with frequency. But then it is hard to normalize that, because increasing weights may lead to very large values if the high frequency contents become very large. So instead, we reversed it. Z0 K over modulus of K, and sum over all coefficients, normalized by sum of all the Z0 K, normalized Fourier coefficient values, and 1 minus that, and we call this the Fourier descriptor, Fourier descriptor based shape factor, and this is limited to 0 to 1. So we wanted to have a normalized value. It is invariant to translation, rotation, starting point, and contour size because of the other normalization already done. Increases as the object shape becomes more complex and rough within the range 0 to 1. So it is in a way low pass filtering here, and then normalizing, and 1 minus that. So 1 minus low pass, it's not exactly high pass, but it just gives you the opposite sense. If you were to multiply by K, then you'll be sensitive to noise, and we didn't want that. So it's a bit strange, but you will see how it works. I'll go back and show that table again with the shapes later. Fractional concavity I already mentioned, so I'll skip this. I showed that picture earlier. So let's look at another feature that one of my students, Naga Mudigonda, he developed for his part of his PhD work. Analysis of spicularity. We said malignant tumors have these spicules. The longer the spicule and narrower the spicule, the stronger the indication of malignancy. Broad, they're not spicules, but macro lobulated contours, if you want to call that a spicule, they won't be long. The excursion out of the main part of the object, the mass, will be short, and this angle, if you want to measure that, will be broad. So narrow spicules having narrow angle at the vertex and long spicule length indicate malignancy or higher probability of malignancy. So we proposed a speculation index to characterize this property, which was described by the radiologist. I'll skip all this. You can read this later. I'll show the picture, and that is easier. And we'll go back to some details if needed. So here is that malignant tumor again, and we have a spicule here between points of inflection. The plus marks are points of inflection. These are additional vertices of the polygonal model. So if you consider this spicule, the angle contained here is 36 degrees. But to measure the angle, we need to make put some rules here, do some processing, because it's not just two lines. There's 1, 2, 3, 4, 5 segments. So which angle do you take? So that is another question that comes up. In the case of this, which is not exactly a spicule, the internal angle here is 170 degrees. So that's almost a straight line. So then we will put them all as spicules because we don't know which one. We could reject some of these, but we said, well, if the angle is so large, the weight will be low. But some of these are a bit hard to characterize. We've got 108 degrees, and this is the average angle computed was 94 degrees. So there is an algorithm we developed for to obtain the angle in an average sense, which is like this. If a spicule, or if a part of a contour between 2 points of inflection, if that is a spicule and there are no other points of no other vertices of the polygon, there are only 2 sides and 1 angle, no issue. That's easy. You just take that angle. But if you have 2 points of inflection and in between there are other vertices of the polygonal model, then there are so many angles. If you have 5 sides, there are 4 angles, internal angles. So which angle do you take? So we said, well, we will compute a threshold by averaging all the internal angles. And those angles that are less than the threshold will be kept, and we will average them. The other angles are rejected. The length of the spicule is putting all of them together. Length is not a problem. Here also length, you just add up all the lengths of those sides of the polygon. This could be modified. Because we're averaging, we're getting some numbers that are large. There are several angles that could pass this threshold test. So you may define it to be something else if you want to avoid this smoothing of some kind. Anyway, we get all these angles, and it's all described there. We don't have to go through that. I have described using this figure. Then, if Sn and theta n are the length and angle of spicules, and there are n spicules, then we defined the speculation index as 1 plus cosine of theta n Sn. And if the angle is very small, the value of cos will be large. And we are adding 1 as a bias because the angle could be more than 90 degrees. So we are raising the cosine by adding 1. And then multiplying by the spicule length, normalized by the total of the spicule lengths or the boundary of the whole contour. So let me show some results. That's simply the procedure. I think the Fourier factor, I already showed the Fourier factor in that table. I'll go back and show that. The Fourier factor, Fourier descriptor-based factor, agrees with this ranking that Liang had put in: 0.14, 17, 18, 19, 24, 25, 30, 36, 42. In that, this one. As I said, you may rank order these in a different way based on your perception of sharpness or complexity of some manner. Okay? The other compactness and moment-based factors did not give a monotonically increasing sequence of numbers for this set of objects. Is this correct? We could discuss that, but there is a sequence here. Okay. Liang Shen also did shape analysis of calcifications. I showed you a method to detect calcifications earlier. And then we measured statistics in terms of the density, and also we got a number of shape factors. Malignant calcifications tend to be rougher in shape than benign calcifications that have smooth contours. So here we have 143 calcifications, 79 malignant and 64 benign. The benigns are these circles, the malignants are these plus marks. Compactness, normalized CF. This is the Fourier factor, increasing that way. This is the moment factor. So there is good separation here. Compactness itself is doing very well, surprisingly. Sometimes as engineers and scientists we say, okay, so something more sophisticated and equations that look well, we go in a certain direction. We think that we are developing something fantastic or something original and novel and complicated, not too simple. But the simple measure of compactness has worked very well. The moment-based factor has worked well. The Fourier factor has worked well. In fact, the Fourier factor at one of our contacts, I don't remember which university, I think they were in Boston at that time. So they asked for this code and we gave the Fourier factor, and in their work that turned out to be the best shape factor in the analysis of tumors. So the Fourier factor has worked well in other applications in breast cancer detection. So separability of these clusters, malignant versus benign, is what we are looking for. To analyze this, you need pattern classification. That is the chapter, the last chapter in the book. In that we have given some results of pattern classification using different methods. So here all I want to show is how these can achieve separation of these samples. Different pattern classification methods will give you different accuracy measures. We have used neural networks and we got nearly 100% accuracy with this data set. So another way to represent the features is in terms of mean and standard deviation. We didn't mark outliers. These box plots, one could also mark outliers. Benign and mean for malignant, and this is the standard deviation bar. So there is good separation. Fourier factor, benign, malignant. Again, there is good separation. Compactness, the best perhaps. So the simple measure of compactness is doing very well. And even with the standard deviation taken into account, there is substantial separation between the two clusters. Okay. These are not bad, they're working, but do we need these on top of that? No, not for this data set. But if you get a much larger data set from other mammograms, other patients, other subjects, perhaps you will need more features. So based on this one study, we cannot say this is the best and throw the others out. Shape analysis of breast masses and tumors, we had multiple data sets from the MAIAS database on which Dr. Desertel drew the contours and we obtained the shape factors. We did not analyze the shape factors from our mass detection algorithms. We just showed what you can detect and the accuracy of detection. We didn't use them in shape analysis. Instead, Dr. Desatel, our radiologist, had drawn these contours on the mammograms. So we took those and did shape analysis, taking these to be accurate. So we got one data set from the MAS database, which is this, and we got another database from the Foothills Hospital in Calgary, and later on we got another database of digital mammograms from Italy. So we did multiple tests. I won't show all of them. Here's one, and B is benign, M is malignant by biopsy. So that is the ground truth. And you can see most of the benign ones are almost round and oval. Some benign ones have a couple of spicules. Some malignant ones don't have spicules, but they are microlobulated. There is one benign that is coming at the end of this. This is rank ordered by the feature CF, compactness, normalized, fractional concavity, speculation index. Those are the three features combined. Rank ordering, most of the benigns are there, most of the malignants are there, but there is some mixing. There are some benign masses with some speculation. Dr. Desatel questioned that this is the MAS database from the UK. He said he questioned this, whether they are really benign. But we don't have access to any more information than just the mammogram and the label.
The majority of the malignants have speculations.
Yes, yes. So speculation index, malignants higher. Compactness, malignants higher. Fractional concavity, malignants higher. Benigns are here, but some benigns have gone there. For this data set, only 54 cases. You need hundreds of them before you can conclusively say that one is better than the other. We have another data set. In some of our other papers, we have added more after this was published. So I don't have all of that here. If you are interested, I can send you some of our research publications with larger data sets and cross-validation. You train on this data set, test on the other one, try various feature selection processes, try various pattern classification methods. We have some other papers. So when you compute a number of features, suppose you compute 10 features. Here I'm showing 3. It's convenient to plot. If I have 10, I can't plot. Are they really mutually independent in the sense, are they giving you different information, or are they simply correlated? So you need a feature selection method to say, I have computed 10 features, but 3 of them are perhaps highly correlated with a few others, so only perhaps 7 of them are useful, or maybe only 4 of them are useful. A feature selection method will check for such correlation amongst the features you have developed, given the classification knowledge, and then you can reduce the data set at the size of the feature vector. Otherwise, your pattern classification algorithm may not work efficiently. The higher dimension may cause problems in pattern classification. And then there are so many pattern classification methods that depend upon the distribution. Are these Gaussian distributed? Are they multivariate Gaussian? What is the separability? So the result that you get depends upon the subsequent methods you apply. And if you have a big neural network with many layers, you will get 100%. With more training, more indentations in the contour, it depends on how you perceive the details. And if you're using a digital image processing method to get the contour, noise will affect the resolution and quality of the contour. In clinical practice, it is not common to draw the contours of tumors and organs. Radiologists don't do that in clinical practice. So one could say they don't have experience in doing that, but instead of that, we will say, well, that is not what they normally do. And if you ask them to do it, yes, after drawing some of them, they can do. In many of our studies, radiologists have drawn contours of calcifications and masses, tumors, and various parts of the body. I'll show you in landmarking. But that is not what is done in clinical practice. Malignant tumors typically exhibit poor definitions of their margins. I've shown you some. So where do you draw the boundary? It is difficult. So identification and drawing of their contours is difficult either manually or by computer methods. You will only get approximate contours. So hand-drawn and computer-detected contours may contain imperfections and artifacts, so you may need to filter them. And there could be significant variations between contours drawn by different individuals and the same individual over time. But you won't find 10 radiologists to draw the contours of 1,000 mammograms 10 times each. It's impossible, although some reviewers may ask you to get such data. It's not possible. It should also be recognized that the contour of a 3D entity, such as a tumor, as it appears on a 2D image, such as a mammogram where the breast is compressed and you get a projection, a radiographic shadow, 2D of a 3D object, depends upon imaging parameters and projection geometry. You take it this way or that way or this way, the shape will be different. So spiculated tumor, if it has spicules only in certain directions, they could all get integrated along the path of propagation of the X-rays, and you may not see anything in the image. Unlikely, but some of these spicules at least may disappear in the process of obtaining a 2D projection of a 3D body. And in some projects we have said, well, let's get the 3D data set and do the same thing in 3D. And I thought, well, doing in 3D may help and give us better results, but in some projects we got poorer results, and there are a few reasons there. In CT and other modalities of imaging, at least previously, the resolution between slices was not good. You could get high resolution in a plane, but not between planes. So 3D representation did not have isotropic resolution. The new scanners do. Most new CT scanners give you at least 1 millimeter, some of them may be even better, in all 3 dimensions. But then, are there spicules in all 3D? We don't know. It is very difficult for a radiologist to confirm that if the tumor really has spicules in all 3D. Radiologists have viewed the images only in 2D, the mammograms. So, in some cases, the 3D analysis did not give us any better result. That was a bit of a surprise, but it all depends on many factors of imaging and data acquisition and what really exists in 3D versus what has been seen in 2D and documented.
In phantom modeling, phantom, to do in 3D anyway, so 3D, right? Speculations are there.
Yeah. We could do tests with phantoms. We have done with nuclear medicine. I showed a simple phantom. We had other phantoms of the ventricle, and we could insert what would behave as a tumor or what would behave as a blockage. But that is specifically for nuclear medicine imaging. There are mammographic phantoms too, but they are 2D. So we have 3D phantoms. But to create a phantom with spicules and so on is not so easy. So contours of biological entities such as tumors present overlap in their characteristics between categories. Benign and malignant, we saw they overlap depending upon the database and how accurately they were classified by the radiologist or the pathologist. Those categorizations, benign and malignant, were done by the pathologist in biopsy. Now the radiologist could go wrong. They may have 95% accuracy, let's say. Pathologists could also possibly go wrong. There have been situations where pathologists have not done a good job. Are they 100%? No. And how about the sample acquired in biopsy? If the needle is not put in the correct place, you may draw a normal tissue sample out and miss the tumor, or the sample taken may not demonstrate the presence of cancer. So the pathologist, if correct, will say benign. So there are possibilities of other stages of this analysis going wrong. So that when we put a data set together like this, there could be errors in some other place also. What is important is we need to include other measures representing other image characteristics such as texture, gradient, and so on that should complement shape. Shape is only one thing, one aspect of this analysis. It is not the end of the story. Okay? That is the end of this chapter. It's a small chapter. Any questions on this shape analysis?
When we use deep learning kind of methods, we need the delineation by the experts, radiologists. Anyway, radiologists, they have their own personal or subjective kind of thing, as you said. We can automate that also using these type of things. That may be used as a kind of a ground truth.
Automate to what? Detection?
Instead of radiologist delineating that, you can use some kind of a descriptors like this, where it gives a good result probably. So that can be used as a ground truth for the deep learning.
Yeah. We can use results of segmentation using multiple methods and then let the radiologist choose which one is the best and mark that as the ground truth. Is that what you meant? Yeah. Instead of actually drawing the...
Radiologist for delineating everything is too time consuming and too tedious process.
Yeah.
So,
with the Dennis Guglielmo, we also developed some graphical user interfaces, GUIs, so where the initial segmentation result is displayed with the mammogram and tools were provided to manipulate the contour. So to ask the radiologist to draw the entire contour may be difficult, or it may be difficult or too time consuming or too much effort and not worthwhile. But if you give an initial segmentation by one of the methods we will see later on for detection of tumors, or you saw the fuzzy set and all that, then you may say, well, could you please modify this? Just pull and push a few and fit Bezier or spline curves, and you can do that even in some basic software. Adjust, and then you can generate such ground truth, not completely drawn by the radiologist, but corrected, automatically detected contours, corrected and accepted or authenticated by the radiologist. Any other comment? Yeah?
So, going back to those stipulated contours, okay. So, were there instances where, the regions were not appropriately identified? Like, your approach was, purely, classical, like classical approach. So when identifying those, maybe like the tumors or something, so must it always fit? Because all examples you showed, it was like the approach was, efficient. Like, were there instances where it didn't fit? Like,
Yes. I will show you some. In chapter 8, again, we have another method for detection of tumors, where I'll show where the methods worked and where they failed. In fact, right at the beginning, I showed that one picture, which is the cover illustration of the book, where the contour obtained by the computer method was not precise, and I showed you where it is good and where it is not good. So I'll show you some more examples. And if you want more examples, you'll have to refer to some of our papers or the theses of my students. But you will see some more examples. The fuzzy examples I gave you, not all of them were good. No. The benign one was good, but the malignant ones, some extra regions were included, some regions were lost, and after fusion it became better. But the initial results, no, they're not perfect, no. They work to some extent, and they do fail in certain parts. Speculations are hard to include if they are 50 speculations. Not all of them will be included. I'll show you some more examples of mass detection in another chapter 8. Is that what you meant? Yeah. Okay. Any other question or comment? We will switch to texture. As I mentioned, I'm skipping some parts. Some fine details I've skipped, sometimes a few pages, that you could easily read if you're interested in such detail. Unless you're going to implement, you don't need such detail. The general concepts I have explained. I've been going a little faster to create some space for the research seminars at the end. And if there is more time, I'll include a couple more topics that are not in that original list. With 10 hours for the first 3 modules and so on that I put, they're approximations. The course I give in Calgary has a total of 36 hours, but each hour is only 50 minutes, and that's over 13 weeks. So it's a little hard to estimate how that course goes and how this goes. So if I go a little too fast, please stop and ask questions, either during the lecture or after. And by going a little faster, I'll have time to talk about other research projects where you will see the practical application of some of these theoretical foundations. And here also I've been showing practical applications. Okay, we looked at shape analysis, and we also noted at the end that shape by itself is not everything. All the internal details have been thrown out. All the details of the surrounding regions have been ignored. So just shape can give you some information, but not all. So we noted at the end we need additional measures to get better representation of whatever it is, tumor or calcification or some part of the body. And texture is one such measure that takes into account variations in intensity, grayscale, density, whatever the parameter of the image represents. So there are several examples of texture: wood, cloth, brick, and so on. This is texture, this is repeated texture, the same thing happening, different color too. And there is texture there, those stripes, vertical. And on the wall, there isn't any texture here, but there's no brick here. If there is brick, you will see some type of rough texture. Clouds have some texture. So wood has some grainy texture here. So there are various types of texture, and you may categorize them as periodic and random. Periodic could be quasi-periodic, not exactly periodic. This is periodic, but you don't find such periodicity in a biological being. So if there is repetition of a texture element at almost regular periodic intervals, then you call it periodic or ordered. Ordered texture is another name. And the elements of such a texture are called textons, like these are textons. What is a texton? Maybe this blue line and green line. It's hard to say, or you may say it is the little square. It's up to you as to what you are seeing. You can say these are arrangements of little squares, green and blue and white. So then the texton is a little square. In that case, a texton is that big stripe. Brick walls and floors with tiles are examples of periodic texture. The same thing is appearing here, the same tile. If no texton can be identified, texture element, texel or texton, such as clouds and cement wall surfaces, there is some roughness, but you can't see any, there is some graininess, but there is no geometric pattern or motif. In some shirts, floral design, there are the same motif is repeated. Then that is the texton. But in the case of a cement wall surface with some roughness, that is random. There's a book by Rao on texture analysis, and we have used some of his methods. And there he includes the category of weakly ordered or oriented texture. And oriented texture is so common in medical images, and oriented patterns are common, that when I started writing this book, we had already done some work on oriented pattern analysis. I started putting them all together, and that became quite a big chapter. So you will see, oriented pattern analysis has many applications in biomedical image processing. And Rao took or showed these examples, or discussed these examples. Like here, I don't have much left there, but here is sort of oriented pattern, wood grain, brush strokes in paintings. He said these are all oriented patterns. It's not always like that. There could be different orientations. Texture could also be related to visual or tactile sensation. When you feel the surface, you may feel some texture, and that is tactile. Fine, coarse, smooth, granular, periodic, patchiness, mottled, or preferred orientation too. So some of these, if it is not just a picture, but a real object, you may be able to feel, so it is tactile also. So this is something based on what we see. But Haralick and others said texture is statistical, or you can describe texture using statistical measures related to the spatial distribution of gray level variation. The spatial variation actually is not included, it's just a histogram, but there is co-occurrence. So by taking pairs of pixels, or pixels with a certain separation, a little bit of spatial dependency is brought into account. So Haralick's papers have been very popular, and Haralick and others, colleagues, and their papers have had huge numbers of citations. So about citations, I want to tell you, whenever I mention Haralick, I remember this. When Google started coming up with these H index and citation record and all that, some 20 years ago, I didn't know that. One of my colleagues who was very much into this came and said, we should do all assessment of professors, departments, and so on must be done using this index, that index, and impact. And okay, I don't know that. I have never seen that. And then he said, your impact or whatever that number is very good. I said, okay, good. I hadn't seen that. And then we started looking at this on a routine basis. Go to Google Scholar, I got 2 more click and be happy. So I have, it's getting close to 20,000, let's say. At that time, maybe I had 10,000. My friend said, this is good. I said, okay, I'm happy. And then I saw some other papers. And this paper by Haralick has more than all of my papers in my whole life combined. One paper. And the papers by Hu on moments, and the thresholding technique by Otsu. They're short communication papers, but they have more. So then I said, wow. So I tell such stories to my students. What are the term? What's the term? Ego boosters and ego busters. So I look at my number, I say, 15,000. So my ego is boosted. Then I look at Haralick and one paper, and the balloon is pricked. So one should look at the global picture. So in biomedical images, texture does appear, different types of texture. Oriented texture is common in medical images due to the fibrous nature of muscles and ligaments. Muscles have muscle fibers. We can't see them. X-ray images won't show the muscle fibers. They are very thin. But the ligaments and ducts in mammograms show up in the breast, show up in mammograms. And blood vessels, veins, ducts, nerves they are sort of curvilinear structures. They're linear in a small portion, but in a full organ, they will be curvilinear. A preferred or dominant orientation is associated with the functional integrity and strength of such structures, as I said about ligaments. I'll show that later on when we go to chapter 8, which is completely on oriented texture. Ordered texture is found not so much in the human body, but skins of reptiles, snake skin, the same pattern appears. But there is some size variation, orientation variation. It's not exactly periodic. In the retina, there are some patterns that are repetitive. In the cornea, the compound eyes of insects and honeycombs. A honeycomb perhaps is the best example. But I tried to get pictures, and I only got honeycombs that were artificially manufactured. They do that and put that in the whatever that box is for the bees, and the bees go there and do their stuff. But later on I did find some, but they were not showing what I wanted to see. Liver and other such organs are made up of clusters of parenchyma, tissue that are of the order of 1 to 2 millimeters in size. The pixels in CT images used to have 1 by 1 millimeter. Nowadays they are better. But suppose your imaging system has resolution of the order of the size of the parenchymal clusters. Then, with ultrasound imaging, the wavelength of the probing radiation is of that order. But again, technology has changed. Ultrasound also is now into the 4-5 megahertz range. So under these conditions, when the wavelength of the probing radiation or the resolution of your imaging system is of the same order of magnitude, not the same, but order of magnitude of the clusters present, tissue clusters, then there is speckled and random texture. So random texture is more common. So this is part of the liver of a patient, the speckled and mottled appearance. I zoomed in. The size of each image is 55 millimeters square. That's the true size. That's the kidney in a CT image. These are CT images. This is the spine in a CT image. There is some randomness in variation. I wouldn't call it random texture, not as much as that, but there is some variation. This is not texture. These boundaries are not texture. But what is inside here could be taken to be some sort of texture. And this is oriented texture, branching patterns in the lungs. So that is a different type of texture by itself. Oriented, well, yes, there are some oriented patterns, but they keep branching, so you have all orientations eventually. Parts of mammograms, each part is, these three are 60 millimeters square, this is 40 millimeters square. So this is oriented, but there is a preferred orientation there is a preferred orientation here, but this is random, cloudy. You don't see the ligament structure, the fibroglandular structure here. But this is also a part of a mammogram. So within the mammogram, you could have random texture, oriented texture here. That orientation is not clearly seen there. Here it is sort of mixed up. There are oriented parts here and there. So that is what is oriented texture. Periodic, this is endothelial cells in the cornea. This is part of a fly's eye. Each one of them is an eye of the fly. And this is the belly of a cobra. This is periodic. That is sort of periodic by itself, but different pattern. But this, because of the curvature, the projected image shows these with distortion due to projection. Otherwise, I suppose they are of the same size and shape. So this is periodic texture in biological, not biomedical, but this could be medical if they use it for some diagnostic application. There are some interesting models for the generation of texture. How do you generate texture? Interestingly, I wanted to study this, and because I have also studied speech signal processing when I was a grad student at IISc Bangalore, I took a course on speech signal processing. I remembered some of that, and these models and speech generation models have very similar patterns. There are similarities between speech and text generation according to this spot noise model. The types of sounds produced by the human vocal system are voiced, unvoiced, and plosive. Voiced sounds like ah, ee, oo, they are periodic or quasi-periodic. There's a wave like that and it repeats. The waveform changes with the type of the vowel, but if I just change the pitch, I say ah, ah, or higher pitch, the waveform remains the same, but the interval, the pitch will change. Unvoiced is one of them is a fricative, like S and F and J. Or I shouldn't say S. S has A at the beginning, which is a vowel. So I should simply say S, like a snake. That is a fricative, or J. So that is random, but it is filtered random noise. And plosive, where we stop, close the mouth, and go P or T or K also to some extent. So there's those who call plosive or stop signals, where the signal is stopped and then suddenly there is a burst. The first two types get the plosives out because it's a discontinuity in the signal. It's a transient, so you deal with that separately. The first two types, voiced, unvoiced, are the two important types, and they are modeled as the convolution of an input excitation signal with a filter. And the model is that we have the vocal system here, and we are sending puffs of air. We are pushing air from the lungs through here, and we have the vocal cords. If the vocal cords are engaged and they vibrate and open and close, we are producing the voice sound like ah. There is repetition, you can feel here ah, and you can feel the vibration. So the air coming from here is modulated, and we get that signal. When we say s or f, then there is no engagement of the vocal cords. They don't vibrate, the glottis. We are simply pushing air through a constriction like s. The constriction is here. Or f, it's near the lips. So when pushing air through a constriction, you are modifying the spectrum of the input, which is random. So you are filtering, but it is still a random signal. There is no definitive waveform to that. The excitation signal is quasi-periodic when we use the vocal cords to create voice sounds, or random in the case of unvoiced sounds. So this is the standard speech signal generation process: random excitation or quasi-periodic excitation. If you use random, you get unvoiced. If you use quasi-periodic, you get voiced. The vocal tract from here to the lips and to the nostrils, that acts as a filter. And how you shape it determines the speech you are producing. A funny thing you can say here is all the speech, my entire course and all the lectures, all the songs, all the music produced, it's just hot air. You're pumping air through. But hot air means rubbish. So it is air being modulated. The modulation is important. The same can be done here. In the Texton model proposed by Ulish and others, we have random field of impulses, random excitation, random field of impulses, 2D, and quasi-periodic excitation, a periodic train of impulses or pulses. Here, ordered field of impulses. And select between the two, and there is a filter, which is a texture element or texton or spot filter, a point spread function. Same model, and you get a textured image either with random or ordered patterns. And the texton could be isotropic, it could be a flower, it could be a line, it could be an oriented pattern, it could be anything. Texture may also be modeled as the convolution of an input impulse field with a spot or texton that acts as a filter, like speech. There is no physical vocal tract there, it is just a picture. So this is, not Eulish, Van Wyk, the spot noise model for synthesizing random textures. So the Fourier spectrum of the spot acts as a filter that modifies or modulates the spectrum of the 2D random field. Convolution becomes multiplication in the frequency domain. Ordered texture may be generated by specifying the basic pattern or texton to be used and a placement rule. The placement rule need not be periodic. You say, I want this pattern repeated. Like a flower, put here, there, and keep stamping. That's how they make saris and printing, block printing, or clothes with the same block is printed on cloth. Typically periodically, but there could be other patterns where it is not periodic or quasi-periodic, and you just have to say, put it here, 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 and that means you're putting an impulse at those locations, convolving with the spot. Convolution will copy the spot at every impulse. So then that spot becomes a filter. It acts like a filter. Okay, let's stop here. I'll have some more examples coming up. Coffee here, or shall we just break anyway?
3 o'clock.
I'm sorry?
3.
Oh, 3. Sorry. I was thinking about yesterday, I suppose. Yesterday I had a small lunch perhaps. Okay, we'll continue. So essentially, the spectrum of the noisy random texture image will be the spectrum of the spot filter, because it is the other input spectrum of random noise is flat. So here is a noise field, computer generated, and its spectrum, I took the Fourier transform, it's almost constant. This is not constant. There are some variations here. When you map for display, you will see some variations, but that is supposed to be constant. So here are 2 spots, circles, 2 circles, approximate circles. Their Fourier transforms we saw earlier. The Fourier transform for circle is a Bessel function with this ring-like structure and with aliasing artifacts there, or some high frequency artifacts, because these are not perfect circles, they are on a discrete grid. And if you convolve this with that noise field, each time you generate a noise field, it's different. In some cases, I generated a noise field and kept the same and convolved. So if I convolve with this with the noise field, I get this. If you convolve with that, you get this. So these patches are a little bigger than here. So this is filtered noise. And look at the spectrum of this. The spectra of these 2 images are the spectra of the spot multiplied by the spectrum of the noise, which is flat. It's essentially constant. So the spectra of the texture patterns are essentially the same as the spectra of the spot. Okay? It's a square patch, and that's the texture you get, the spectrum of the square, and this is 2D sync function, the spectrum of that. This was convolved with the same noise pattern, and the spectrum of this is essentially the same. Some hash pattern, and the texture, and this and that are essentially the same. Okay. Ordered texture, as I said, you are just placing the same pattern, and you can say there is a certain pitch or repetition rate or distance of separation between the copies of the texton you place in the x and y directions. And that is also convolution of the impulse field with the texton. So the difference between the ordered and the random texture lies in the structure of the impulse field. One uses quasi-periodic field of impulses. The other uses random noise. Random noise is also a bunch of impulses. Every pixel is like an impulse. If you were to break a signal into an impulse train, we saw earlier, you can represent any signal as a bunch of weighted impulses. The same in 2D. So one is a periodic train of impulses or periodic field of impulses. The other is random noise. The spectral characteristics of the texton act like a filter that modifies this. Orthogonal to that, you will see concentration of energy because of the sinc function corresponding to that line. If it is a thick rectangle, then it will be a 2D sinc function, but one axis will have more depending upon the orientation and thickness of that line pattern. So you can provide line segments or oriented motifs, not a flower that is isotropic, but a line. And then you get oriented patterns, like this. I hope you can see that. There's a line there. That's the texton. When I convolve that with the noise field, I get that. That's oriented texture. Lines of various intensities. The Fourier transform of the texton and the image. But for some scaling factor and noise in computation, they are the same. Okay? Analysis of texture could be done using statistics or structure. The two main branches of analysis of texture are statistical and structural. Structure implies the use of measures to represent the texton and how they are placed. You need to identify some pattern in order to describe structure. But you can also say it is composed of line patterns like this and so on. But there is no specific placement rule for this ordered texture I showed just now, this oriented texture rather. If you have some other texture, you can say this is placed above that and left and right, there are these things, and that becomes structural analysis. Parallax measures are based on statistical analysis. But before we go to that, let's look at some basic texture. Basic measures of texture in terms of statistical measures. We could start with the simple moments we have already seen. The kth central moment mk is L minus mu f to the power of k PL. PL is the PDF, but only one gray level at a time. So zeroth order histogram, as we talked about earlier, turned into a PDF. L is the gray level, mu is the mean to the power of k. If k is 2, then that is the variance. There should be a 1 over, no, this is PDF, so there is no 1 over n. Mu is LPL, the moment with only L here. So the variance is a second order square here, L minus mu. So this is important as a measure of inhomogeneity, in the sense there is gray level variation. That's all you can say. Skewness, the third moment normalized by m2 to the power of 3 over 2, or the square root of the third, the standard deviation raised to the power of 3. Or kurtosis, the fourth moment with standard deviation raised to the power of 4. M2 is variance. Standard deviation is square root of that. So skewness and kurtosis indicate that the PDF is not symmetric. It is skewed towards one side. They are basic statistics, but we need to recognize what is important in the given application, what is the distinction between the categories, benign, malignant, or so on. In vertebral compression fractures, we found kurtosis to be useful. I'll show you that later on. But high order moments are affected by noise or error in the PDF or in your measurements, and they may not be reliable. But going up to kurtosis is commonly done. There should not be any difficulty up to the fourth moment, but if you go further, then noise becomes an issue. In mammography, Bing and others computed the skewness of histograms of parts of mammograms. An average skewness measure was computed for each image by averaging the section-based skewness measures for a mammogram. Mammograms of breasts with increased fibroglandular density, known as dense breasts, were observed to have histograms skewed towards higher density. There are more pixels with higher density values. That indicates higher breast density. And if that persists with age, if the breasts are dense at an increased age, that would indicate susceptibility of the development of cancer. Not that it will happen, but increased susceptibility. So mammograms of fatty breasts tended to have positive skewness, whereas higher density gave negative skewness. So that was shown to be a good feature, just one feature. So the skewness measure was found to be useful in predicting the risk of development of breast cancer related to higher breast density or tissue density in the breast. So that's a basic application of one of these four very basic statistical measures. Now, Harrelix measures are not based on that PDF of 0th order, but instead taking pairs of pixels into account. So you look for co-occurred so many times, two occurred so many times. Whereas here, you look at pairs of pixels. Given a pixel, you ask what is the value above, what is the value to the immediate neighbors, 1 pixel above, left, right, and bottom. Or you may say, I will use a spacing of 2 pixels. So the current pixel and 2 pixels away, what is that value? And then there are multiple possibilities. A distance of 2 pixels, take all the pixels in the neighborhood and take their joint, okay, 6, 6, and 6, 5, and 6, 4, and 6, 7, and you have pairs of those pixel values. So they are based on the moments of a joint PDF that is estimated as the joint occurrence or co-occurrence of gray levels, known as the gray level co-occurrence matrix. If you have 255 levels, you have 0, 1, 0, 2, 0, 3, 0, 255, 1, 0, and so on. There are 255 square possibilities of pairs. Now you could also take 3 at a time, 4 at a time, and so on. Then you get to higher and higher order moments, statistical combinations. We saw that earlier in talking about measures of information. It's not just PL, but P, L1, L2, L3. 3 levels together, or L1, L2, L3, L4, 4 levels together. But how are they placed? How is that string placed in space? You need to define a pattern. Here, you need to define in terms of displacement. What is the distance between this pixel and the other pixel you're considering to make a pair? And what is the angle? Above, below, left, right, or some diagonal, whatever angle. So 2 parameters, distance and angle. If you don't care for the angle, you can say any adjacent pixel. Left, right, top, bottom, doesn't matter. They're all equally adjacent. You count them all. Put them all into one matrix. Sometimes that is done. Sometimes you take angle into account in forming the GCM, gray level co-occurrence matrix. It is also called spatial gray level dependence matrix, SGLD matrix. So you compute for various orientations and distances. So the GCM could be defined as P, capital P, the count of occurrences of L1, L2 separated by d theta. D is distance, theta is angle, like in the radial coordinates or polar coordinates. The probability of occurrence of the pair of gray levels L1, L2 separated by a certain distance d and angle theta. So GCMs are constructed by mapping the gray level co-occurrence counts or probabilities based on the specified spatial relationships at angles theta and scanning the image with the distance d, left to right, top to bottom. Now, neighboring elements in natural images tend to have high correlation or nearly the same values. So GCMs tend to have large values along the diagonal of the main diagonal of the matrix and around them. If a pixel has the value 55, quite likely the neighboring pixels are 55, 54, 57. You don't get 200 or 0 there. Those values could occur somewhere else in the image, unless you're at an edge. And low values away from the diagonal. So these matrices have some general properties. So for an image with b bits per pixel, we have L going 2 to the power of b gray levels. The GCM is of size L by L. So if you have 256 gray levels, this will be 256 square. If you have 10-bit quantization, 1024, then 1024 square. And with CT images, if you have 12-bit, then it is that square, 2048 square. No, 2048 is 11, that is 4096 square. So fine quantization to, it's right here, I'm jumping ahead. With 2 to the 12, 4096 in medical images could lead to really large gray level co-occurrence matrices. But with such fine quantization, you may not find pairs of values. There will be large differences, and you may want to re-quantize such images to a smaller number of gray levels and compute the GCM with a smaller matrix size, re-quantize to maybe 8 bits or even 6 bits. Then you may get better properties free of noise. In a noisy image with fine quantization, the GCM may not give you a good number of counts in many of the bins. So in practical applications, we need to consider this. If you have a 1000 by 1000 image with 12-bit quantization, you have 1 million pixels, but you have 4096 square bins in the gray level co-occurrence matrix. That's a mismatch there. So you want to reduce the number of gray levels to a relatively small number before computing the GCMs by re-quantizing, averaging and re-quantizing, maybe some filtering. GCMs are commonly formed for unit pixel distances and the 4 directions, 0, 45, 90, 135. That is top, bottom, left, right. And if you want 8 connectivity, you can consider the 8 connected corners in the 3 by 3 neighborhood. But the distances are not equal. We should bear in mind if any distance related measure is to be taken, then left, right, top, bottom distance is 1, but the diagonally connected elements, the corners, have a distance of √2. Mostly that doesn't matter, but in some cases that may be required. Well, this is my right eye. You have seen my picture earlier. I took that piece, and it's a 16 by 16 pixel image, and I re-quantized to 3 bits per pixel. So the values are between 0 and 7, and those are the values. And now you take, this is 1, so you have 1, 1, 1, 0, and come here 1, 1, 1, 1, 1, 1, and so on. Or take this, you have 3, 1, 3, 4, 3, 1, 3, 1, you have 0, 1, 0, 1, 0, 1, 0, 2. So like that you scan the image and make this co-occurrence matrix. The current pixel, and here I used the next pixel below. I didn't add all of them. I said only looking below, so it's in a way causal, so I cannot do it for the last row. So here I said this is 1, 0. I didn't take that. This is 1, 1, 1, 1, and so on. So the direction is looking downward in the array. So the next pixel below, 0 through 7, these are the counts. Along the main diagonal, you have not so. There are some large entries here. This is the eye, and there are rapid changes, black and white parts. So we don't have that main diagonal having large values, but there are some large values here. But if you go to the ends, these probabilities are lower. So yeah, in the middle somewhere here, you have large values. 0 and 7, 0 and 6 have not occurred. And similarly, 6, 0, 7, 0, 5, 0, they have not occurred. Okay? So that's the co-occurrence matrix, looking 1 pixel below the current pixel. If you do that for looking pixel to the right or top, and you'll get something different. Or if you say, I'll add all of them, I'll consider all of them, then you will get something different, average of all directions. If you don't want to be sensitive to direction, you may say, I'll take all 4 connected neighbors and count all of them. Okay, Haralick then said, Haralick and colleagues, they're known as Haralick's texture, but there are co-authors. This was PL1, L2 is the GCM. You normalize by the total number of values. So you call that treat it like a PDF, bivariate PDF, PL1, L2, small p. Now you take the marginals, integrate or sum this in one direction, L2, and sum in the other direction, L1, you get Px and Py. These are called marginals. And then Px plus Yk. Add the two, and PL1, L2, L1 going 0 to L minus 1, L2, all of the whole range, but L1 plus L2 must be equal to K. Then that is called X plus Y, K. There's only one index now. And similarly, X minus L1 minus L2 must be equal to K in magnitude. The sum of all these probabilities for all L1, L2 with that condition. So these were computed from the given GCM, and then a few measures were defined. Some of the basic measures one can understand easily and interpret. Some of the other measures, they are hard to interpret, and I have gone through their papers and they have not described what exactly the other measures represent in terms of visual features or any concept that we can understand and relate to. They are just statistical measures. But P square, it's like a second moment, P square L, like energy. So this is called the energy feature. That's easy to understand. A homogeneous image has a large number of entries along the diagonal, and large values go there, and the other values are small. An inhomogeneous image will have small values spread over a large number of GCM entries. So that leads to low F1, the other one gives you large F1. Large F1 means homogeneous, low means inhomogeneous texture. Contrast, you apply a weight K square where K is L1 minus L2 multiplied with the probability, with the P L1 L2, which is a normalized GCM. Putting the weight K square, which is based on the difference of the gray levels. If the difference is more, and for large differences, the probability of occurrence of such pairs is large, this will be large. The correlation measure, L1, L2, P L1, L2 minus the mean, mu x, mu y. Mu x, mu y, and sigma x, sigma y are the standard deviation values of the marginals, Px, Py. So this is the normalization factor. This is weighting by L1, L2 for P L1, L2 and subtract the means. So this is interpreted as correlation. The sum of squares, it's like a variance, L1 minus mu f, PL1 L2, and inverse of that, 1 over 1 plus L1 minus L2. To avoid 0, dividing by 0, you add a 1 here. PL1 L2 will remain. So these are all moments of the PDF. This is a PDF. And you can take moments, you integrate the PDF with some weight. So what is the weight? That is the argument for the expectation operator or the moment that you are taking. It's like expectation. All these statistical moments, but these are the controlling factors. That is the PDF. Here, you are taking the difference in the denominator, so it is a measure of homogeneity. If the differences are large, it means heterogeneity, but it's in the denominator, so it is homogeneity. Some average, they took the px plus yk, moment of that. Some variance, the variance of that, px plus y, the probability of the sum of those values. Some entropy, so there are a few measures of entropy. Entropy is p log p, as we have seen. But which probability? X plus y, log of that. And another measure, this GCM, normalized GCM, PL1, L2, log of that. So these are just entropy measures. Here the sum PDF is taken, here the original PDF is taken. And then the difference, X minus Y. Another entropy, difference entropy. These measures are a bit hard to interpret. The 12, 13, 14, I didn't find any explanation or physical interpretation of these in the original paper or anywhere else. So the previous measure, no, they're not here. They'll come later. There are entropies HX1, XY, and XY1, and the max of HX, HY. That is 12, and 13 is this, where these entropies are, XY1 is the entropy of PL1, L2, but log of the PX and PY. And here you have the product PX, PY, and log of that. So they define two more measures of entropy and combine them here. Why or what does that represent? I could not find a suitable interpretation. And the last one is further complicated. Complicated in the sense something is being done, but there's no interpretation given. The probability PL1K, PL2K divided by PXL1, PYK. I found this expression a bit awkward. There is something wrong, but I checked with my colleague and checked with other sources. I even wrote to Haralick. This, I don't know if that should be K. Yeah, that should be outside. It is independent of this summation. It should not be inside. Maybe they wanted it to be K.
With reference to L1.
But why is it inside? It should be outside. The summation is on K, and take that out, independent of K. It's with reference to L1, yes, but there is no meaning given to any of this. So in practical applications, there are many papers that have said, well, we tried all the 14 and the first 3 or 4 or 5 were adequate. So there are many papers where they have used only the first 4 or 5 of these measures, which can be easily interpreted. The others have not found much application because they're hard to interpret, or maybe they haven't worked well. We have also used all of them. We have included them in our projects because we need to compare the performance, and they may contribute in some sense to our pattern classification problem. So these are popular measures, all the shape factors we saw, whose moments, and so on, and Haralick's measures. If you don't use them, the reviewers may question, did you try these and did you compare? So at least for that purpose. But these are known, well known and well established, so you could try them, and if they work, that's good. If the dependence of texture upon angle is not of interest, GCMs over all angles may be averaged into a single one. As I said, instead of just looking at the pixel below the current one, you can say, well, I'll count the one above, left, right, and below, and take all of those 4 counts and throw them all into the same GCM. Then you're not sensitive to orientation. Distance D, it should be taken into account according to the sampling interval and pixel size and the size of the texture units of interest, or you downsample the image. Resample or downsample the image and recompute. And at some resolution you may get good results and not at other resolutions. We found that in mammograms, a resolution of 200 micrometers is good. Not 100, not 50, not more than that. 400, no. So there is a certain limit in the resolution at which these measures work well. Texture. If you use too fine resolution, then you may not get meaningful counts of a co-occurrence. And if you use too coarse resolution like 400 or 800 micrometers, then you will lose information. So the angle and distance d and theta need to be accounted for depending on the application, the resolution of your image, and the expected spatial size or dimensions of the patterns of interest. So normalization to a range such as 0 to 1 over the data set may be beneficial. Or you may normalize by dividing by the standard deviation of each feature.